Hello, how's everyone doing? Let me just change to full screen. Okay, so last stream I learned about where is it? Yeah, iterators and algorithms. So I did some sorting stuff, sorting bubble array and the I mean bubble sort and the selection sort. These two chapters are under construction, but I'm going to read them anyways. I already read this chapter, but I'm going to read dynamic allocation and maybe some of function pointers as well. Okay, I've already saved the PDF, so let's start with 19.1. Dynamic memory allocation with new and delete. The need for dynamic memory allocation. C++ supports three basic types of memory allocation, of which you've already seen two. Static memory allocation happens for static and global variables. Automatic memory allocations happens for function parameters and local variables. Memory for these types of variables is allocated when a relevant block is entered and freed when the block is exited as many times as necessary. Or for these ones, memory for these types of variables is allocated once your program is run and persists throughout the lifetime of your program. Dynamic memory allocation is the topic of this article. Both static and automatic allocation have two things in common. The size of the variable array must be known at compile time. Memory allocation and deallocation happens automatically. Most of the time, this is just fine. However, you need to come across situations where one or both of these constraints cause problems, usually when dealing with external users or file input. If we declare the size of everything at compile time, the best we can do is to try to make a guess the maximum size of variables we will need and hope that's enough. So character name, let's hope their name is less than 25 characters, and record, let's hope it's less than 500. Let's hope they're less than 40 monsters, and so on. This is a poor solution. First, it leads to wasted memory if the variables aren't actually used. Second, how we tell which bits of memory are actually used. How do we tell which bits of memory are actually used? For strings, it's easy. A string that starts with a /0 is clearly not being used. But what about Monsters 24? Is it alive or dead right now? Has it even been initialized in the first place? That necessitates having some way to tell the status of each monster, which adds complexity. Third, most normal variables are allocated in a portion of memory called the stack. The amount of stack memory for a program is generally quite small. Visual Studio defaults the stack size to 1 megabyte. If you exceed this number, stack overflow will result. On Visual Studio, you can see this happening when running this program. So allocate 1 million integers, probably 4 megabytes. Then this will cause an error. Okay. Fourth, and most importantly, it can lead to artificial limitations and or array overflows. What happens when the user tries to read 600 records from disk, but we have only allocated memory for maximum 500? Either we have to give the user an error, only read 500 records, or in the worst case, overflow the record array and watch something bad happen. Fortunately, these problems are easily addressed via dynamic memory allocation. Dynamic memory allocation is a way for running programs to request memory from the operating system when needed. This memory does not come from the program's limited stack memory. Instead, it is allocated from a much larger pool of memory managed by the operating system called the heap. On modern machines, the heap can be gigabytes in size. To allocate a single variable dynamically, we use the scalar non-array form of the new operator. So new int dynamically allocate an integer. In the above case, we are requesting an integer's worth of memory from the operating system. The new operator creates the object using that memory, then returns a pointer containing the address of that memory that has been allocated. Most often, we will assign the return value to our own pointer variable so we can access the allocated memory later. So int pointer new integer, dynamically allocate an integer and assign the address to pointer so we can access it later. We can then dereference the pointer to access the memory. Okay, so the value of whatever is stored here is now 7. If it wasn't before, it should be clear. It should now be clear at least one case in which pointers are useful. Without a pointer to hold the address of the memory that was just allocated, we would have no way to access the memory that was just allocated for us. Note that accessing heap allocated objects is generally slower than accessing stack allocated objects because the compiler knows the address of stack allocated objects. It can go directly to that address to get the value. Heap allocated objects are typically accessed via pointers. This requires two steps. One is to get the address of the object from the pointer, and another is to get the value. How does dynamic memory allocation work? Your computer has memory that is available for applications to use. When you run an application, your operating system loads the application into some of that memory. This memory used by your application is divided into different areas, each of which serves a different purpose. One area contains your code, another area is used for normal operations, keeping track of which functions were called, creating and destroying global and local variables. We'll talk more about those later. However, much of the memory available just sits there, waiting to be handed out to programs that request it. Wait, when you run an application, your operating system loads the application into some of that memory. This memory used by application is wait. This is my memory. The operating system loads the application into some of that memory. Okay. So my application loads into some of that memory. And it's divided into 4 areas. So each of which serves a different purpose. One area contains your code. So another area is used for normal operations, keeping track of which functions were called, creating and destroying local variables. Okay. Normal operations. Code, normal operations. When you dynamically allocate memory, you're asking the operating system to reserve some of that memory for your program's use. If it can fulfill this request, it will return the address to that memory to your application. From that point forward, your application can use this memory as it wishes. When your application is done with the memory, it can return the memory back to the operating system to be given to another program. Unlike static or automatic memory, the program itself is responsible for requesting and disposing of dynamically allocated memory. The allocation and deallocation of stack objects is done automatically. There's no need for us to deal with memory addresses. The code the compiler writes can do this for us. The allocation deallocation for heap objects is not done automatically. We need to be involved. That means we need some unambiguous way to refer to a specific heap allocated object so that we can request its destruction when we are ready. And the way we reference such objects is via memory address. When you dynamically allocate a variable, you can also initialize it via direct initialization or uniform initialization. So this is direct initialization with the brackets, and this is uniform initialization. Deleting a single variable. So this is done via scalar non-array form of the delete operator. Delete. Assume pointer has previously been allocated with operator new, so delete pointer. Return the memory pointed to by pointer to the operating system. And then pointer is set to null pointer, set the pointer to null pointer. But isn't pointer deleted? Or does delete only work with the value of pointer? Return the memory pointed to by pointer PTR to the operating system. Okay, so wait. You have this. Suppose this is the memory, like a bunch of sequential memory. And then you do new pointer. So this pointer variable is equal to 5, which is the address of this. Let's see. This here is 6. This here is 4. This here is 3. This is the memory address. Memory address 3, memory address 4, 5, and 6. And this is the pointer variable. So when we do delete, I think freeze this, right? This is free available, this is free available, this is free available, this is being used. But when we do delete pointer, this is now free, but this pointer variable is still assigned to 5. So we need to set it to null pointer. What does it mean to delete memory? The delete operator does not actually delete anything. It simply returns the memory being pointed to back to the operating system. The operating system is then free to reassign that memory to another application or this application later again. Wait, isn't the heap reserved for one process or for one program? What does it mean like it can reassign to another application? Although the syntax makes it look like we are deleting a variable, this is not the case. The pointer variable still has the same scope as before and can be assigned a new value just like any other variable. Note that deleting a pointer that is not pointing to a dynamically allocated array may cause bad things to happen. C++ does not guarantee about what will happen to contents of a deallocated memory or to the value of the pointer being deleted. In most cases, the memory returned to the operating system will contain the same values it had before it was returned, and the pointer will be left pointing to a new deallocated memory. A pointer that is pointing to a deallocated memory is called a dangling pointer. Dereferencing or deleting a dangling pointer will lead to undefined behavior. So new integer, and then the value is 7, and then delete pointer, like the value of this is 7, and now that they deleted it, the operating system sees this as a free memory. Now stdc out, dereferencing a dangling pointer will cause undefined behavior. Or we don't know what the operating system actually did. Maybe it kept it as 7, or maybe it did something else. So most likely it will return 7 again. Trying to delete the memory again will also lead to undefined behavior. this. Let's see if this works. Let's put it in release. I don't think I actually need this delete pointer over here. The value of 7 was previously assigned to allocated memory will probably still be there, but it's possible that the value at that memory address could have changed. It's also possible that the memory could be allocated to another application. Trying to access that memory will cause the operating system to shut the program down. Um, Process exited with code. This. Okay, it causes an error. Deallocating memory may create multiple dangling pointers. Consider the following example. So new integer. So integer over here. Other pointer. So if you're deleting this pointer, pointer is null pointer. The other pointer is dangling. First, try to avoid having multiple pointers point at the same piece of dynamic memory. Second, when you delete a pointer, if that pointer is not going out of scope immediately afterwards, set the pointer to null pointer. Pointer new can fail. When requesting memory from the operating system in rare circumstances, the operating system may not have any memory to ground the request with. By default, if new fails, a bad alloc exception is thrown. If this exception isn't properly handled, the program will simply terminate with an unhandled exception error. In many cases, having new throw an exception is undesirable, so there is an alternate form of new that can be used instead to tell new to return a null pointer if memory can't be allocated. This is done by adding constant std no throw between the new keyword and the allocation type. So as with std no throw, value will be set to null pointer if the integer allocation fails. In the above example, if new fails to allocate memory, it will return a null pointer instead of the address of the allocated memory. Note that if you then attempt to dereference this pointer, undefined behavior will result. Consequently, the best practice is to check all memory requests to ensure they actually succeeded before using the allocated memory. Integer pointer to integer value. Ask for an integer's worth of memory. Null pointers and dynamic memory allocation. Null pointers are practically useful when dealing with dynamic memory allocation. In the context of dynamic memory allocation, a null pointer basically says no memory has been allocated to this pointer. This allows us to do things like conditionally allocate memory. So if pointer isn't already allocated, we can check this with not pointer. Then we can allocate new memory. Dynamically allocated memory stays allocated until it is explicitly deallocated or until the program ends. However, the pointers used to hold dynamically allocated memory addresses follow the normal scoping rules for local variables. This mismatch can create interesting problems. So integer, so pointer to integer. I think when do something is done, then this pointer variable is deleted. but the memory address of this is still like allocated. It's not free. This function allocates an integer dynamically but never frees it using delete. Because pointer variables are just normal variables, when the function ends, pointer will go out of scope, and because pointer is the only variable holding the address of the dynamically allocated integer, when pointer is destroyed, there are no more references to the dynamically allocated memory. This means the program has now lost the address of the dynamically allocated memory. As a result, this dynamically allocated integer cannot be deleted. This is called a memory leak. Memory leak happens when your program loses the address of some bit of dynamically allocated memory before giving it back to the operating system. Memory leaks eat up free memory while the program is running, making less memory available, not only to this program but to other programs as well. Programs with severe memory leak problems can eat all the available memory, causing entire machine to run slowly or even crash. Although memory leaks can result from a pointer going out of scope, there are other ways that memory leaks can result. For example, a memory leak can occur if a pointer holding the address of the dynamically allocated memory is assigned another value. So enter value. So pointer is assigned some other address. So the address of this is now lost. This can be fixed by deleting the pointer before reassigning it. Relatedly, it is also possible to get memory leak via double allocation. Operators new and delete allow us to dynamically allocate single variables for our programs. Dynamically allocated memory has dynamic duration and will stay allocated until you deallocate it or the program terminates. So next topic. I'll open the next page as well. Dynamically allocating arrays. In addition to dynamically allocating single values, we can also dynamically allocate arrays of variables. Unlike a fixed array where the array size must be fixed at compile time, dynamically allocating an array allows us to choose an array length at runtime. In these lessons, we are dynamically allocating C-style arrays, which is the most common type of dynamically allocated array. To allocate an array dynamically, we can use the array form of new and delete. So enter a positive integer, size t length, enter length, and then array new integer or size length. Use array new. Note that length does not need to be a constant. Stdc out. I just allocated an array of integers of length. Use array delete to deallocate array. So this I'm guessing it frees up the whole array of size length. Because we are allocating an array, C++ knows that we should use the array version of new instead of the scalar version of new. Essentially, the new square bracket operator is called even though the square bracket is in place next to the new keyword. The length of the dynamically allocated arrays has type size t. If you're using a non-constant expression integer, you will need to static cast to size t, since that is considered an arrow conversion and your compiler will want otherwise. Note that because this memory is allocated from a different place than the memory used for fixed arrays, the size of the array can be quite large. You can run the program above and allocate an array of length 1 million without issue. dynamically deleting arrays. When deleting a dynamically allocated array, we have to use the array version of delete, which is delete with square brackets. This tells the CPU that it needs to clean up multiple variables instead of a single variable. One often asked question of array delete is how does the array delete know how much memory to delete? The answer is that array new keeps track of how much memory was allocated to a variable so that array delete can delete the proper amount. Unfortunately, this size length isn't accessible to the programmer. In lesson 17.8, you learn that a fixed array holds the memory address of the first array element. You also learn that a fixed array can decay into a pointer that points to the first element of the array. In this decayed form, the length of the fixed array is not available, but otherwise there is little difference. A dynamic array starts its life as a pointer that points to the first element of the array. Consequently, it has the same limitation in that it does not know the length or size. A identically dynamic array functions identically to a decayed fixed array. If you want to initialize a dynamically allocated array to 0, the syntax is quite simple. Prior to C++11, there was no easy way to initialize dynamic array to non-zero value. This means you had to loop through the array and assign element values explicitly. However, starting with C++11, it's now possible to initialize dynamic arrays using initializer list. So initialize a fixed array before C++11, initialize a dynamic array since C++11. To prevent writing the type twice, we can use auto. This is often done for types of long names. Dynamically allocating an array allows us to set the array length at the time of allocation. However, C++ does not provide a built-in way to resize an array that has already been allocated. It is possible to work around this limitation by dynamically allocating a new array, copying the elements over and deleting the old array. However, this is error-prone, especially when the element type is a class. Consequently, we recommend avoiding doing this yourself. Use std vector instead. So, write a program that asks the user how many names they wish to enter. Okay, so what is this? Using uninitialized memory pointer. Okay. So std cout enter length. And then actually as to integer, no, std size underscore t length local variable is not initialized, and then std cin length. And then ask the user how many names they wish to enter. How many names to enter? Dynamically allocate a std string array. So std string array is new std string, hold on, include string and it's a pointer to string, and then for integer I is equal to 0, I is less than or equal to length, then I plus plus or plus plus I maybe, and this is supposed to be brackets like that, and let's see, std cn. Now first I will ask them to enter name, enter name space space uh, std string name name, and then um, maybe like this. Whoops, not 0, it should be I. uh, no, int is fine. So let's see what the issue is. Oh wait, it has to be like this. I keep forgetting. Array size must be specified in new expressions without an initializer. Length. Also, I need to delete it, right? Five. Bob. One, two, three. Oh, I entered four. These are four names. And delete. Alright. And I will do print names std string array std string and then for no wait, no, I'll just do length here. Yeah, length std cout array I. std cout printing names. Then print one character. Let's see. And then print names. I should do it here. Array length. Conversion from size t to int. Std size t. So let's do 3. First, second, third. First, second, third. Why did it take so long to delete the array? Call std sort this to sort the names and print the sorted list. Yeah, what's this? Is allocated with array new but deleted with scalar delete. Oh, maybe like this. Why is the color different? I need to change the syntax highlighting. But let me just see if the delete. No, it's not correct. Yeah, this is correct. So let's do 8. Right. Now we have to do std sort. Where is sort? Like, is it in the algorithm? Algorithm std sort. Is it this? Okay, I can't remember the sorting part. Let me see the answer. Sort array and then array plus length. But where is it stored? I can't remember. IOStream, maybe iterator. No, there's no syntax highlighting. I can't remember. STM algorithm. It's an algorithm. Algorithm sort. STD sort. array plus length maybe. Oh, no, I just have to write the arguments. Um, and I have to use getLine. Std getLine. So std white space and then names I. Okay, so get names count, auto names new string length, get name names length, enter name number this. Okay, I need to get used to using getLine. So stdcn std white space name well for me it's array. So array I enter name number I plus 1. Yeah. Let's see. Five number 1. Why is it taking so long? Yeah, why can I still type? Oh, because I'm doing this twice. Cn and hold on. String name. Let's remove this and let's remove this. So enter 5. Let's try this, this, and then this. Yeah. So next lesson, destructors. Let's just open the next chapter. And then the next chapter as well. A destructor is another special kind of class member function that is executed when an object of that class is destroyed. Whereas destructors are designed to initialize a class, whereas constructors are designed to initialize a class, destructors are designed to help clean up. When an object goes out of scope normally or a dynamically allocated object is explicitly deleted using the delete keyword, the class destructor is automatically called if it exists to do any necessary cleanup before the object is removed from memory. For simple classes, a destructor is not needed because C++ will automatically clean up the memory for you. Like constructors, destructors have specific naming rules. The destructor must have the same name as the class preceded by a tilde, cannot take arguments, has no return type, and only one destructor. Generally, you should not call a destructor explicitly since there are rarely cases where you will want to clean up an object more than once. However, destructor may safely call other member functions since the object isn't destroyed until after destructor executes. So we have int array, m array, and then m length. So we have a destructor that dynamically delete the array we allocated earlier. So they allocate the array dynamically and then they delete it in the destructor. If you compile the above you can get the following error. Then you either remove this flag from your compile settings for this example or add the following two lines. We will discuss this delete for members in lesson 14.14. I forgot what this does. Let me see if it works for me. Let's see. I don't think I need this, but anyways. So value of element 5 is array get value. So it's setting the set value count plus 1. So at that index, it's setting the value of the index basically. Okay, value of element 5 is 6. Okay, it works. Okay, constructor and destructor timing. As mentioned previously, the constructor is called when an object is created and destructor is called when an object is destroyed. In the following example, we will use cout statements inside the constructor and destructor to show this. Okay. Global variables are constructed before main and destroyed after main. RAII. Resource acquisition is initialization. It is a programming technique whereby resource use is tied to the lifetime of the objects with automatic duration. In C++, RAII is implemented via classes with constructors and destructors. A resource is typically acquired in the object's constructor. That resource can then be used while the object is alive. The resource is released in the destructor when the object is destroyed. Primary advantage of RAII is that it helps prevent resource leaks of all resource holding objects, as all resource holding objects are cleaned up automatically. The int array class at the top of this lesson is an example of a class that implements RAII. A warning about stdexit. Note that if you use stdexit function, your program will terminate and no destructor will be called. Be wary if you're relying on your destructors to do necessary cleanup work. But within the program end, if this ends the program, then the destructor would have to be called, right? Pointers to pointers and dynamic multi-dimensional arrays. A pointer to pointer is exactly what you would expect, a pointer that holds the address of another pointer. Normal pointer to an integer is declared using a single asterisk. A pointer to an integer is declared using two asterisks. A pointer to a pointer works just like a normal pointer. You can dereference it to retrieve the value pointed to. And because that value is itself a pointer, you can dereference it again to get the underlying value. These dereferences can be done consecutively. So double dereference. Note that you cannot set a pointer to a pointer directly to a value. This is because the address of operator requires an L value, but the ampersand operate value is an R value. However, a pointer to a pointer can be set to null. Pointer to pointers have a few uses. The most common use is to dynamically allocate an array of pointers. This works just like a standard dynamically allocated array, except the array elements are of type pointer to integer instead of integer. Another common use for pointers to pointers is to facilitate dynamically allocated multi-dimensional array. For a review, unlike two-dimensional fixed array, which can easily be declared like this, dynamically allocating a two-dimensional array is a little more challenging. You may be tempted to try to do something like this, but it won't work. There are two possible solutions here. If the rightmost array is a constant expression, you can do this. Let's see. The parentheses are required so that the compiler knows we want an array to be a pointer to an array of 5 integers. Or we can have 5 over here, which in this case is the first row of 7-row multidimensional array. Without the parentheses, the compiler wouldn't be able to interpret this as a pointer to array 5, which is an array of 5 integer pointers. And this is a good place to use automatic type deduction. Unfortunately, this relatively simple solution doesn't work if the rightmost array dimension isn't a compile time constant. In that case, we have to get a little more complicated. First, we allocate an array of pointers, then we iterate through the array of pointers and allocate a dynamic array for each array element. Our dynamic two-dimensional array is a dynamic one-dimensional array of dynamic one-dimensional array. So array pointers to pointers is new integer pointers of 10. These are our rows. And then looping through 10, we have new integer 5. These are our columns. So an array of 5 integers. We can then access our array like usual. With this method, because each array column is dynamically allocated independently, it's possible to make dynamically allocated two-dimensional arrays that are not rectangular. For example, we can make a triangle-shaped array. Oh, so it's like, so the array is they have 10. So 1, just have dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then each array has count plus 1. So the first one has 1, and then the next one has 2, and the next one has 3, and then 4, and then 5. Right. So the inner array, so it's an array of arrays, but the inner array has different lengths. Deallocating a dynamically to allocated two-dimensional array using this method requires a loop as well. So delete array count and then delete array. Note that we delete the array in the opposite order that we created it. If we delete the array before the array columns, then we would have to access deallocated memory to delete array columns. Because allocating and deallocating two-dimensional array is complex and easy to mess up, it's often easier to flatten a two-dimensional array into one-dimensional array of size x times y. Simple math can then be used to convert a row and column index for a rectangular two-dimensional array into a single index for a one-dimensional array. Much like we can use a pointer parameter to change the actual value of the underlying argument passed in, we can pass a pointer to a function and use that pointer to change the value of the pointer it points to. However, if you want a function to be able to modify pointer argument, what a pointer arguments point to, this is generally better using a reference to a pointer instead. It's also possible to declare a pointer to a pointer to a pointer. This can be used to dynamically allocate a three-dimensional array. However, doing so would require a loop inside a loop. We recommend avoiding using pointer to pointers unless no other options are available. Okay. I think I will just read this and then I will end the stream. The void pointer, also known as a generic pointer, is a special type of pointer that can be pointed at objects of any data types. A void pointer is declared like a normal pointer using a void keyword as the pointer's type. A void pointer can point to objects of any data type. So you have an int, you have a float, and the pointer stores the address of an integer, it stores the address of float, and then it stores the address of something. Because a void pointer does not know what type of object it is pointing to, dereferencing a void pointer is illegal. Instead, a void pointer must first be cast to another pointer type before the dereference can be performed. The next obvious question is, if a void pointer doesn't know what it's pointing to, how do we know what to cast it to? Ultimately, it is up to you to keep track of it. Void pointers can be set to null pointer. Because a void pointer does not know what type of object it is pointing to, deleting a void pointer will result in undefined behavior. If we delete a void pointer, static cast it back to the appropriate type first. It is not possible to do pointer arithmetic on a void pointer. This is because pointer arithmetic requires the pointer to know what size object it is pointing to, so it can increment or decrement the pointer appropriately. Note that there is no such thing as void reference. This is because void reference would be of type void ampersand and would not know what type of value it referenced. It is generally a good idea to avoid using void pointers unless absolutely necessary, as they effectively allow you to avoid type checking. However, very occasionally, you may still find a reasonable use for void pointer. Just make sure there isn't a safer way to do something using other language mechanisms first. What's the difference between a void pointer and a null pointer? A void pointer is a pointer that can point to any object but does not know what type of object it points to. A void pointer must be explicitly cast to another type of pointer to perform indirection. A null pointer is a pointer that does not point to an address. A void pointer can be a null pointer. Right. Anyways, I will end the stream here, and next stream I'll start learning function pointers, all the function stuff, chapter 20 basically. Okay, I'll see you guys next time then. Bye.